In physics, jerk, also known as jolt, surge, or lurch, is the rate of change of acceleration. That is, the derivative of acceleration with respect to time, and such the second derivative of velocity, or the third derivative of position. Jerk is defined by any of the following equivalent expressions. Where is acceleration, is velocity, is position, is time. Jerk is a vector, and there is no generally used term to describe its scalar magnitude. According to the result of dimensional analysis of jerk, length time 3, the SI units are ms3. There is no universal agreement on the symbol for jerk, but is commonly used. Newton's notation for the time derivative is also applied. Because of involving third derivatives, in mathematics differential equations of the form are called jerk equations. It has been shown that a jerk equation, which is equivalent to a system of three first-order, ordinary, nonlinear differential equation is in a certain sense the minimal setting for solutions showing chaotic behavior. This motivates mathematical interest in jerk systems. Systems involving a fourth or higher derivative are called accordingly hyperjerk systems. Physiological effects and human perception of physical jerk, the smooth movement and also the rest state of an alert human body is achieved by balancing the forces of several antagonistic muscles which are controlled across neural paths by the brain or sometimes across reflex arcs. In balancing some given force, the post-central gyrus establishes a control loop to achieve this equilibrium by adjusting the muscular tension according to the sensed position of the actuator. If the load changes faster than the current state of this control loop is capable to supply a suitable, adaptive response, the balance cannot be upheld, because the tensioned muscles cannot relax or build up tension fast enough and overshoot in either direction, until the neural control loop manages to take control again. Of course, the time to react is limited from below by physiological bounds and also depends on the attention level of the brain. An expected change will be stabilized faster than a sudden drop or increase of load. So passengers in transportation, who need this time to adapt to stress changes and to adjust their muscle tension, or else suffer conditions such as whiplash, can be safely subjected not only to a maximum acceleration, but also only to a maximum jerk, so not to lose control over their body motion, thereby endangering their physical integrity. Even where occupant safety is not an issue, excessive jerk may result in an uncomfortable ride on elevators, trams and the like, and engineers expend considerable design effort to minimize it. As an everyday example, driving in a car can show effects of acceleration and jerk. The more experienced drivers make up for a smooth, beginners provide a jerky ride. The changing of the gear, especially with a foot-operated clutch, offers well-known examples. Although the accelerating force is bounded by the engine power, an inexperienced driver lets you experience severe jerk, because of intermittent force closure over the clutch. High-powered sports cars offer the feeling of being pressed into the cushioning, but this is the force of the acceleration. Only in the very first moments, when the torque of the engine grows with the rotational speed, the acceleration grows remarkably and a slight whiplash effect is noticeable in the neck, mostly masked by the jerk of gear switching. The beginning of an emergency braking lets the body whip forward faster than the achieved acceleration value alone would accomplish, but this is not apt to an experiment. A highly reproducible experiment to demonstrate jerk is as follows: brake a car starting at a modest speed in two different ways, apply a constant, modest force on the pedal till the car comes to a halt, only then release the pedal. Apply the same, constant, modest force on the pedal, but almost before the halt, reduce the force on the pedal, optimally releasing the pedal fully, exactly when the car stops. The reason for the by far bigger jerk in the first way to brake is a discontinuity of the acceleration, which is initially at a constant value, due to the constant force on the pedal, and drops to zero immediately, when the wheels stop rotating. Note that there were no jerk when the car started to move backwards with the same acceleration. Every experienced driver knows how to start and how to stop braking with small jerk. See also below in the motion profile, segment 7, deceleration ramp down. For some remarks on how the human perception of various motions is organized in the proprioceptors, the vestibular organ and by visual impressions, and how to deceive it, see the article on motion simulator. Forces and path derivatives. Position itself, zeroth derivative. The most prominent force associated with the position of a particle relates via Hooke's law to the rigid stiffness of a spring. This is a force opposing the increase in displacement. Speed, magnitude of the first derivative. A particle, moving in a viscous, fluid environment experiences a drag force, which, depending on the Reynolds number and its area, ranges between being proportional to up to being proportional to according to the drag equation. Where is the density of the fluid, is the speed of the object relative to the fluid, is the cross-sectional area, and is the drag coefficient a dimensionless number. The drag coefficient depends on the scalable shape of the object and on the Reynolds number, which itself depends on the speed. Acceleration, magnitude of the second derivative. The acceleration is according to Newton's second law. Bound to a force, via the proportionality given by the mass. Higher derivatives. In classical mechanics of rigid bodies there are no forces associated with the higher derivatives of the path, nevertheless not only the physiological effects of jerk, but also oscillations and deformation propagation along and in non-ideally rigid bodies require various techniques for controlling motion to avoid even destructive forces. It is heavily reported that NASA in designing the Hubble telescope not only limited the jerk in their requirement specification, but also the next higher derivative, the jounce. For a recoil force on accelerating charged particles emitting radiation, which is proportional to their jerk and the square of their charge, see the Abraham-Lorentz force. A more advanced theory, applicable in relativistic and quantum environment, which takes care of self-energy is provided in Wheeler-Feynman absorber theory. Jerk in an idealized setting, assuming Newton's laws of motion and rigid bodies implies the possibility of discontinuous accelerations. Having a jump discontinuity in acceleration results in a Dirac delta in the jerk, scaled with the height of this jump, making the jerk unbounded. Integrating jerk over time generally gives the according acceleration. Doing so across such a Dirac delta reconstructs exactly the jump discontinuity in acceleration belonging to the Dirac delta. Something unbounded might look unphysical at the first glance, and, of course, does not happen in real-world environments, because of deformation, granularity at least at the Planck scale, that is quanta effects, and other reasons, but the usual setting of a point mass, moving along a piecewise smooth and as a whole continuous path, suffices for this phenomenon in classical mechanics. Assume a path along a circular arc with radius, which tangentially connects to a straight line. The whole path is continuous and its pieces are smooth. Now let a point particle move with constant speed along this path, so its tangential acceleration is zero, and consider the acceleration orthogonal to the path. It is zero along the straight part and along the circle. This gives a jump discontinuity in the magnitude of the acceleration by, and the particle undergoes a jerk measured by a Dirac delta scaled with this value, for purely geometric reasons, when it passes the connection of the pieces. See below for a more concrete application. If we assume an idealized spring and idealized, kinetic frictional forces, proportional to the normal force and directed oppositely to the velocity, there is another example of discontinuous acceleration. Let a mass, connected to an ideal spring, oscillate on a flat surface with friction. Each time the velocity changes sign, the magnitude of the force on the mass, which is the vectorial sum of the spring force and the kinetic frictional force, changes by twice the magnitude of the frictional force, since the spring force is continuous and the frictional force reverses its direction when the velocity does. Therefore the acceleration jumps by this amount divided by the mass. That is, the mass experiences a discontinuous acceleration and the jerk contains a Dirac delta, each time the mass passes through the maximal displacements, until it comes to a halt, because the static friction force adapts to the residual spring force, establishing equilibrium with zero net force and zero velocity. According to the idealized settings above, the effect of jerk in real situations can be approximately described, explained and predicted. The car example relies on the way the brakes operate on a rotating drum or on a disc. As long as the disc rotates, the brake pads act to decelerate the vehicle via the kinetic frictional forces which create a constant braking torque on the disc. This decreases the rotation linearly to zero with constant angular acceleration, but when the rotation reaches exactly zero, this hitherto constant frictional force suddenly drops to zero, as well as the torque, and the associated acceleration of the car. This, of course, neglects all effects of tire sliding, dipping of suspension, real deflection of all ideally rigid mechanisms, etc. A sudden drop in acceleration indicates a Dirac delta in the physical jerk, which is smoothed down by the real environment, the cumulative effects of which are analogous to damping, to the physiologically perceived jerk. Another example of significant jerk, analogous to the first setting, is given by cutting the rope twirling a particle around a center. When the rope is cut, the circular path with non-zero centripetal acceleration changes abruptly to a straight path with suddenly no force in the direction to the former center. Imagine a monomolecular fiber, cut by a laser, and you arrive at very high rates of jerk, because of the extremely short cutting time. Jerk in rotation. Consider a rotational movement of a rigid body about a fixed axis in an inertial frame. The orientation of the solid can be expressed by an angle, the angular position, from which one can express the angular speed as the time derivative of, the angular acceleration as the time derivative of. Deriving the with respect to time, defines an angular jerk. The angular acceleration corresponds to the quotient of the torque acting on the body in the moment of inertia of the body with respect to the momentary axis of rotation. An abrupt change of the torque results in an important angular jerk. The general case of a rigid body movement in space can be modeled by a kinematic screw, which specifies at each instant one vector, the angular velocity, and one vector, the linear velocity. From this the angular acceleration is defined as, and thus the angular jerk. Consider for example a Geneva drive, a device for creating an intermittent rotation of the driven wheel from a continuous rotation of the driving wheel. On one cycle of the driving wheel there is a variation of the angular position of the driven wheel by 1/4 of a cycle, and a constant angular position on the remainder of the cycle. Because of the necessary finite thickness of the fork making up the slot for the driving pin, this device generates a discontinuity in the angular acceleration, and therefore an unbounded angular jerk in the driven wheel. This does not preclude the mechanism to be used in, for example, movie projectors to stepwise transport the film with high reliability and just slight noise. Since the load is very low, the system drives just that part of the film which is within the corridor of projection, so a very low mass, with low friction, at a moderate speed is affected. To avoid the jerk inherent in a single cam device, a dual cam device can be used instead, bulkier and more expensive, but also quieter. This operates two cams on one axis in continuous rotation and shifting another axle about a fraction of a full revolution. The pictures show a step drive by 1/6 and 1/3 rotation, respectively per full revolution of the driving axle. Note that two of the arms of the stepped wheel are always in contact with the double cam, so there is no radial clearance. To follow the detailed operation of the dual cam devices, it is advisable to have a look at the enlarged pictures. Generally, combined contacts may be used to avoid jerk associated with one single follower, for example gliding along a slot and thereby changing its contact point from one side of the slot to the other, by using two followers sliding along always the same, one side each. Jerk in elastically deformable matter. A force acceleration acting on an elastically deformable mass will affect a deformation which depends on its stiffness and the acceleration applied. If the change of this force is slow, the jerk is small, the propagation of this deformation through the body may be considered instantaneously compared to the change in acceleration. The distorted body acts as if it were in a quasi-static regime. It is the common thread, that only a changing force, that is a non-zero jerk, can cause mechanical waves to be radiated. So for non-zero to high jerk, a shock wave and its propagation through the body is to be considered. The left picture shows the propagation of a deformation as a compressional, plane wave through an elastically deformable material. For angular jerk, the deformation waves are arranged circularly and cause shear stress as shown in the picture to the right, which also might cause other modes of vibration. As usual with waves, one has to consider their reflections along all boundaries and the emerging interference patterns, that is destructive as well as constructive interference, which may lead to exceeding boundaries of structural integrity. As a rough estimate, the deformation waves result in vibrations of the whole contraption and, generally, vibrations cause noise, wear, and, especially in resonance cases, even disruption. The picture to the left shows a massive top bending the elastic pole, to which it is connected, to the left, when the bottom block is accelerated to the right. When the block stops accelerating, the top on the pole will start an oscillation under the regime of the stiffness of the pole. This could make plausible how a bigger jerk might excite a bigger amplitude of the oscillations, because any small oscillations are damped before they get reinforced by another amplitude of the shock wave. One can also argue that a steeper slope of the acceleration, that is a bigger jerk, excites bigger wave components in the shock wave with higher frequencies, belonging to higher Fourier coefficients, and so an increased probability of exciting a resonant mode. As a general rule, to reduce the amplitude of excited stress waves, causing vibrations, any motion of massive parts has to be shaped by limiting the jerk, that is making the acceleration continuous and keep its slopes as flat as possible. Since the described effects are almost not amenable to abstract models anymore, the various suggested algorithms for reducing vibrations include still higher derivatives, the jolts, and as a rumor, also the crackle and the pop, or suggest continuous regimes not only for the acceleration, but also for the jerk. One concept is for example shaping the acceleration and deceleration sinusoidal with zero acceleration in between, making the speed look sinusoidal with constant maximal speed too. The jerk however will remain discontinuous in the points when the acceleration enters and leaves its zero phases. Applications: although jerk is not directly involved in Newton's laws, it has to be considered in engineering in various places. Normally, only speed and acceleration are used for analysis. For example, the jerk produced by falling from outer space to the Earth is not particularly useful given the gravitational acceleration changes very slowly. Sometimes the analysis has to include the jerk for a particular reason. Geometric design of roads and tracks. The principles of geometric design apply to the jerk oriented orthogonally to the path of motion, considering the centripetal acceleration. Here as the velocity along the path is assumed to be constant and so the tangential jerk is zero. Any change in curvature of the path implies non-zero jerk, arising from purely geometric reasons. To avoid the unbounded jerk when moving from a straight path into a curve or vice versa, track transition curves are constructed, which limit the jerk by gradually increasing the centripetal acceleration, that is the curvature, to the value that belongs to the radius of the circle and the speed of travel. The theoretical optimum is achieved by the Euler spiral, which linearly increases the acceleration, that is minimal constant jerk. As a design rule a maximum value of 0.5 ams3 and for convenience purposes a value of 0.35 ams3 are recommended in railway design. The picture shows a piece of an Euler spiral leading as track transition curve from a straight line to an arc of a circle. In the real scenario the plane of the track is inclined in the course of the curve and so also this vertical acceleration of the necessary lifting of the center of mass of the rail car has to be considered to minimize the wear on the embankment and the tracks by following a slightly different curve. This has been patented as Wiener curve. Roller coasters are of course also subject to these design considerations, when rolling into some loop. The acceleration values range up to 4g in this environment and it would not be possible to ride loopings without track transitions, as well as one cannot smoothly drive along a line 8 consisting of circles. Any S-shaped curve must contain some jerk-reducing transition. Motion control. In motion control the focus is on straight linear motion, where the need is to move a system from one steady position to another. So effectively, the jerk resulting from tangential acceleration is under control. Prominent applications are elevators in people transportation, and the support of tools in machining. It is reported that most passengers rate a vertical jerk of 2.0 ams3 in a lift ride as acceptable, 6.0 ams3 is intolerable, and for a hospital environment 0.7 ams3 is suggested. In any case, limiting jerk is considered essential for riding convenience. ISO 18738 defines how to measure elevator ride quality with respect to jerk, acceleration, vibrations and noise, but does not venture into defining what are different levels of elevator ride quality. Achieving the shortest possible transition time, thereby not exceeding given limit magnitudes for speed, acceleration, and jerk, will result in a third-order motion profile, with quadratic ramping and deramping phases in the velocity, as illustrated below. This motion profile consists of up to 7 segments defined by the following: acceleration buildup, limit jerk implies linear increase of acceleration to the limit acceleration, quadratic increase of speed, limit acceleration, implies zero jerk and linear increase of speed, acceleration ramp down, approaching the desired limit velocity with negative limit jerk, that is linear decrease of acceleration, quadratic increase of speed, limit speed, implies zero jerk and zero acceleration, deceleration buildup, limit negative jerk implies linear decrease of acceleration to the negative limit acceleration, quadratic decrease of speed, limit deceleration, implies zero jerk and linear decrease of speed, deceleration. Ramp down, limit jerk implies linear increase of acceleration to zero, quadratic decrease of speed, approaching the desired position at zero speed and zero acceleration. The time allotted to segment 4, concerning constant velocity, is to be varied to suit the distance between the two positions. If the initial and final positions are so close together that a complete omission of this 4-segment does not suffice, the segments 2 and 6 with constant acceleration are equally reduced and the limit of speed would not be reached in this variant of the profile. If also this does not reduce the cross distance sufficiently, in a next step the ramping segments 1, 3, 5, 6 are to be shortened by an equal amount and the limit of acceleration is not reached, also. There are also other strategies to design a motion profile, for example minimizing the square of the jerk for a given transition time, to be selected according to the varying applications in machines, people movers, chain hoists, automotive industries, robot design, and many more. For a sinusoidal-shaped acceleration profile, with sinusoidal-shaped speed and bounded jerk also, see above. Jerk in manufacturing. Jerk is also important to consider in manufacturing processes. Rapid changes in acceleration of a cutting tool can lead to premature tool wear and result in uneven cuts. This is why modern motion controllers include jerk limitation features. In mechanical engineering, jerk is considered, in addition to velocity and acceleration, in the development of cam profiles because of tribological implications and the ability of the actuated body to follow the cam profile without chatter. Jerk must be often considered when the excitation of vibrations is a concern. A device that measures jerk is called a jerkmeter. See also, jounce, the derivative of jerk, Abraham-Lorentz force, a force in electrodynamics whose magnitude is proportional to jerk, shock, Wheeler-Feynman absorber theory, notes. References, Sprott J.C. Chaos and Time Series Analysis. Oxford University Press. ISBN A0-19-850839-5. Sprott J.C. Some simple chaotic jerk functions. AMJ Phys 65, 537 €43. Bibcode, 1997 MJPH 65 537 SDOI, 10.1119/1.18585. Retrieved September 28, 2009. Bled G. Making the Cam. Race Engine Technology. Retrieved September 29, 2009. External links. What is the term used for the third derivative of position? Description of jerk in the Usenet Physics FAQ. Mathematics of Motion Control Profiles, Elevator Ride Quality, Elevator Manufacturer Brochure, Patent of Wiener Curve, German, Description of Wiener Curve.